All right, my friends, we are going to look at how to find the area under a curve. In this case, it's y equals x squared. And we are going to find the area of this shaded region between x equals 0 and x equals 2. Well, so by logic, the area under that curve would be the sum of the little bits of area under that curve. A way to write that in what's called integral notation is like this. And what this means, if you kind of read it in English, is the area equals the sum of the teeny tiny bits of area. Well, we're going to carve this thing up into teeny tiny bits that look like these vertical strips, right? And so here is another look at that vertical strip. In the area of that little vertical strip, that little bit of area called dA, to get its area, we'd have to take its height times its width. Well, its height is the height of the function, x squared. That's how far up you go from the x-axis to meet the function y equals x squared. And its width is, well, infinitesimally small, and so we're going to call that dx. And so the area then is going to be the height times the width, or x squared times dx. Well, so then in order to find the total area, we have to sum up all of the x squared dx's. So that's what we're going to do. And what we're going to do is we're going to sum up all the x squared dx's as we sweep x from 0 to 2. Now, when you see this, what you're going to want to do is take the antiderivative of this function. So when you're at this state in trying to solve the problem, the function that's being multiplied by a little bit of length, the x squared here, you're going to find its antiderivative, which is 1/3 x cubed. Now, as a reminder, like how could I check that that's actually the antiderivative? Well, let's try taking the derivative. Bring the 3 down in front. 3 times 1/3 would be 1, and then you reduce the 3 to be an exponent of 2 if you took the derivative. So the derivative of 1/3 x cubed is x squared. And so this is what's called the antiderivative of that function. And what you do is you evaluate the antiderivative at the two endpoints, at 2 and at 0. And so when you do that, you would get 1/3 of 2 cubed minus 1/3 of 0 cubed, giving the area under this curve, which is allegedly 8/3. So what we've done here by sweeping from 0 to 2 is we have added up all these little bits of area, these little rectangular strips of area between 0 and 2. And if you added up all these little patches, these vertical strips of area, you would get 8/3. Well, there's another way that we could have looked at this to find the area under this same exact curve. Maybe we don't feel like carving it into vertical strips. Maybe we feel like carving it into other little bits of area. So again, area is the sum of the little bits of area, which is also basically what this notation is saying. The area is the infinite sum of the infinitesimal little bits of area. But what we're going to do now is, instead of vertical strips, we're going to cut it up into these little bitty squares, okay? Squares of infinitesimal width and height, right? So that little bit of area, which is called dA, this little guy, we have to take its height times its width. Well, its height is a little wiggle in the y-coordinate, and its width is a little wiggle in the x-coordinate. So the height times the width is dy dx. So if we then want to continue and sum up all the little bits of area, we have to sum up all the dy dx's. Now what's different here is two coordinates are going to sweep. Before we were only sweeping the x-coordinate, now we're sweeping both. Well, so we have to look at how far to sweep them. Well, one way we could do this is we could sweep the y-coordinate from 0 up to the function. That would sort of color in a vertical strip here. If we could sweep the y-coordinate from 0 up to the function, right? And then once we've done that, we'll have like a little vertical strip, and then what we'll do is we'll sweep it from x equals 0 to x equals 2. So this is our first, what's called the double integral. We're sweeping two coordinates. So what we're going to do is we're going to take the sum, or we're going to sweep the y-coordinate first, right? So what we're actually doing is we're adding up all the little bits of like vertical or y length between 0 and x squared, all right? So the function that's in front of the dy is really just 1. So we are what's called integrating 1 dy. And so we need the antiderivative of 1, which is just y. If you take the derivative of a y, you'll get 1. And so I've put the antiderivative in there as before. And then what we need to do is evaluate the function y at the endpoints. So you plug in x squared and plug in 0. And so you'll get x squared minus 0, or just x squared. Now the thing to notice conceptually, what actually happened is we added up the little bits of y and we found the total vertical length between 0 and x squared. Well, of course, the total vertical length between 0 and x squared as you go vertically is just x squared. So that's just, again, this total vertical length between the horizontal axis and the function. But now we're right back where we were in the last example. We're adding up all the x squared dx's. So now what we need to do is take the antiderivative of x squared and evaluate it at the endpoints. So again, we're right back where we started. We've got this vertical strip now, and then we just need to sweep it sideways to kind of color in the rest of this area. And so what we're going to do is we need to take the antiderivative of x squared, and that's going to be 1/3 x cubed. And then as before, we need to evaluate it at the two endpoints. So 1/3 2 cubed minus 1/3 0 cubed. And my gosh, you get the same answer. You get 8/3. There's yet another way we could have looked at this. Oh, so by the way, by sweeping the integral over x here, what we've done is we've swept that vertical strip sort of along the x-axis. We've added up all vertical strips which have a height of x squared and a width of dx. And so that's what the second integral in our double integral did. The first integral over y swept it this way, vertically, and then the integral over x swept it horizontally to kind of color in this area. Let's just check out what happens if you were to switch the order. What if we would have swept horizontally first and then vertically second? Let's see what happens. So again, we're going to find the area under the same function between 0 and 2, once again. So the area, once again, is the sum of the little bits of area, which is basically what this notation is saying. Once again, we're going to take our little bits of area to be this tiny little patch. So that little patch has area that can be found by its width and its height. So there's the little patch. Its width is dx. Its height is dy. And so now our little patch of area is dx times dy. And so the same story as before, we need to add up all the dx dys. Well, since two coordinates are sweeping once again, we have to think about how far we should sweep them. So the dx, that means like a horizontal sweep. We're going to add up all the dx's. Well, if we take this little patch here, we kind of want to sweep it horizontally. We got to think, where do we start and where do we stop? Well, we're going to stop at 2. That's kind of obvious. If you're sweeping horizontally, you're going to want to stop at 2. But where do we start? Well, where we start depends on how high we are. If we use a known starting place y, the horizontal location then would be square root of y. That's actually the x, the x coordinate would be square root of y. So we start at the square root of the y coordinate and we sweep all the way over to 2. So that's why the limits on what's called this integral over dx, it goes from root y to 2. Now, before we do this integral, what this integral in purple is actually saying, it's saying add all the little bits of x length between root y and 2. So it just wants to know how far we go when we go from starting at root y and sweep over to 2. Well, spoiler alert, this length is just going to be 2 minus root y. But we'll kind of see this play out. So what we're doing as before with this sort of maroon or magenta colored integral here, we are integrating the function 1 dx, and so we need to take the antiderivative of 1, and the antiderivative of 1 is just going to be x, but then we have to evaluate it at the two limits. And so this will become, you plug in a 2, evaluate x when x equals 2, and then x when x equals root y. So this will evaluate to 2 minus root y. And so that has executed the integral over x. We've swept the x coordinate. Now notice when we do that, when we sweep the x coordinate, we've swept that little patch of area horizontally, and we've ended up with a new area that's the product of its length, its horizontal length rather, which is 2 minus root y, and its vertical in its vertical width, I guess, which is dy. So now, what we're going to do is we're going to add up all these little horizontal strips to sort of color in the rest of this region. And so that's why we're sweeping y from 0 all the way up to 4 to color this in. Well, so once again, we need to take the antiderivative of the function that's in white here, the antiderivative of 2 minus root y. So we need the function for which if we took its derivative, we would get 2 minus root y. Well, that function would be 2y minus 2y to the 3 halves over 3. Now to check it, right, if I take the derivative of the term 2y, I'll just get 2, so that worked. And then if you take the derivative of the second term, y, you'd bring the 3 halves down. Well, 3 halves times 2/3 would just give you a 1. And then you would reduce that exponent to be an exponent of 1 half instead of 3 halves, so you get root y. And then we have to evaluate it at the limits. Well, evaluated at the 0 limit, that will give you nothing. So we really just need to focus on what happens when we shove a 4 in there. And so what you're going to get is, well, 2 times 4 is 8. Let's see, 4 to the 3 halves. Well, first you could take root 4 and then cube it. Well, root 4 is 2, and then if you cube it, you get 8. So 2 times 8 over 3 would be 16 over 3. So 8 minus 16 over 3, or 24 over 3 minus 16 over 3, gives you 8 over 3, which is the same answer that we got before. Well, so there's a little introduction to integrals and even double integrals. What you're doing when you take an integral is you're just adding up a whole bunch of little bits to make a whole. And so in this case, we were adding up a whole bunch of little areas to get an entire area. So really the punchline with what integrals kind of mean is you're summing up a lot of teeny tiny bits to get a whole thing. So here where it says area equals, well, integral dA, the area is the sum of the little bits of area. Well, hopefully you found this thing helpful as a little introduction, and thank you for checking this out.